The rifle sat on the aluminum workbench under fluorescent light, stripped to its major assemblies, upper receiver separated from lower, bolt carrier group laid out in sequence. The barrel, still warm from the test firing range, rested on padded cradles. To an untrained eye, it looked like any AR-15 variant awaiting inspection. But the upper receiver told a different story. Where a standard M4 would show a gas tube running from the front sight base back to the bolt carrier, this receiver showed a channel machined into the metal itself. A piston rod, no thicker than a pencil, sat in that channel. At the muzzle end, a compact gas block housed the piston assembly, a cylinder barely an inch long. The entire gas system occupied the space between the chamber and the muzzle, self-contained and isolated from the action. This was Oberndorf, Germany, 2004. Heckler Koch's development facility, where the company that had engineered the G3, the MP5, and the G36 was now attempting something more constrained and perhaps more difficult, improving someone else's design without abandoning what made it successful. The HK416 project began not with ambition, but with data. Field reports from military units using M4 carbines in extended operations showed a pattern. The direct impingement system, which used propellant gases to cycle the action, deposited carbon fouling directly into the bolt carrier group. In controlled conditions with regular maintenance, the system worked. In desert environments with fine sand, in Arctic conditions with extreme cold, or during intense tactical engagements where cleaning wasn't possible, that carbon buildup created friction that led to malfunction. The engineers at Heckler Koch understood that replacing the gas system meant preserving everything else. The AR-15 platform dominated global military inventory not because of its gas system, but despite it. The modularity, the ergonomics, the manual of arms, the accessory compatibility. These elements had institutional momentum. A new rifle would face budget battles, training overhead, and logistics reorganization. An improved upper receiver that mounted on existing lowers faced none of those barriers. The piston rod on the workbench represented that calculation. Short-stroke piston systems weren't novel. They appeared in the HK416, the FAL, the G36 itself. What was novel was the integration. Making a piston system fit within the AR-15's dimensions while maintaining headspace tolerances, preserving accuracy, and avoiding harmonic interference required treating the barrel and piston assembly as a unified thermal system. Metal expands when heated. A piston, striking an operating rod thousands of times per minute, generates heat and vibration. Those forces had to be managed within margins measured in thousandths of an inch. The test data showed promise. The frequency of operational failures had decreased significantly. Carbon buildup still occurred, but it accumulated in the gas block, forward of the action, where it couldn't impede the bolt carrier's movement. Cleaning intervals could extend from hundreds of rounds to thousands. For units operating in environments where maintenance windows were unpredictable, that margin represented operational capability. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Ernst Mauch had spent 3 decades at Heckler Koch, most of it in small arms development. By 2004, he'd seen enough rifle projects to recognize the difference between innovation and iteration. The HK416 was deliberately the latter. The challenge wasn't inventing a new system. It was disciplining the engineering to touch only what needed changing. The request had come from operators who knew the M4's strengths and limitations intimately. They didn't want a replacement rifle. They wanted the M4 they already knew, but with the reliability they needed when cleaning schedules became theoretical. That clarity of requirement was rare and valuable. Most military projects began with broad capability statements that invited scope creep. This one began with a parts diagram and a red circle around the gas tube. Mauch's team started with dimensional constraints. The AR-15 upper receiver has limited internal volume. A piston system requires a cylinder, a piston, an operating rod, and a return spring. All of that had to fit within the existing receiver envelope without interfering with the barrel nut, the bolt carrier's travel path, or the handguard attachment points. The gas block had to replace the standard front sight base while adding the piston assembly, but it couldn't extend the overall length or require specialized tools for installation. The first prototype worked mechanically, but failed thermally. After sustained use, a realistic test condition, the barrel expanded enough that the piston-to-cylinder clearances tightened beyond acceptable tolerances. The piston bound against the cylinder walls, creating friction that slowed the cycle rate and eventually caused a stoppage. The solution required calculating thermal expansion coefficients for the barrel steel and the gas block housing, then engineering clearances that were loose enough to accommodate heat expansion but tight enough to prevent gas leakage at operating pressure. The second challenge was impact dynamics. In a direct impingement system, gas pressure acts gradually on the bolt carrier through the gas key. In the piston system, the operating rod strikes the bolt carrier, a mechanical impact repeated thousands of times. That impact had to transfer enough energy to cycle the action reliably, but not so much that it accelerated parts wear or created excessive recoil impulse. The mass of the piston, the stroke length, the spring rate, each variable affected system timing. Mauch's background in mechanical engineering served him here. The team built mathematical models of the gas pressure curve, piston acceleration, and carrier velocity. They tested spring rates from different manufacturers. They measured cycle times with high-speed cameras. The goal was a carrier velocity that matched the standard M4's timing, ensuring compatibility with existing buffer weights and springs. Achieving that required iteration on piston mass and stroke length until the energy transfer profile aligned with the baseline. There was institutional pressure. Heckler & Koch's reputation rested on systems that performed. The G3 had equipped dozens of nations. The MP5 had defined its category. The company didn't release products that failed field trials. But the HK416 faced a different test. It had to outperform a rifle that, despite its compromises, had become the standard against which all others were measured. Incremental improvement wasn't enough. The piston system had to deliver measurable, documentable, operationally relevant gains in reliability. By late 2004, the test data supported the design. The HK416 was cycling reliably through sand, mud, and temperature extremes that degraded M4 performance. The carbon fouling that would accumulate in a direct impingement bolt carrier was instead venting forward through the gas block. The mechanism was working as intended. The gas system operates on principles that predate modern firearms. Pressure differentials, mechanical advantage, energy transfer. What makes the HK416's implementation specific is how it manages those principles within the AR-15's architecture. When the device is triggered, the propellant burns, converting chemical energy to expanding gases. Those gases accelerate the projectile down the barrel. Approximately 4 inches from the muzzle, the projectile passes a gas port drilled through the barrel wall. At that moment, chamber pressure is still several thousand pounds per square inch. A portion of those gases escapes through the port into the gas block. The gas block contains a cylinder aligned with the barrel. Inside that cylinder sits a piston, a hardened steel component that fits the cylinder bore with minimal clearance. When gases enter the cylinder, they push the piston rearward. The piston is not attached to anything. It simply slides within the cylinder, constrained by its length to a stroke of less than 1 inch. This is the short stroke designation. The piston moves only enough to impart momentum, then stops. Behind the piston is the operating rod, a separate steel component that extends backward through a channel machined into the upper receiver. The operating rod's forward end sits against the piston's rear face. When the piston moves backward, it strikes the operating rod, transferring kinetic energy. The operating rod continues rearward, driven by that momentum. The operating rod's rear end interfaces with the bolt carrier. Unlike a standard M4 bolt carrier, which has a gas key on top to receive impingement gases, the HK416's bolt carrier has a cup-shaped recess. The operating rod's rear end fits into that recess. When the rod drives rearward, it pushes the bolt carrier with it. The bolt carrier's rearward motion follows standard AR-15 operation from this point. The carrier cams the bolt to rotate and unlock from the barrel extension. The extractor pulls the spent casing from the chamber. The ejector pushes the casing out through the ejection port. The carrier compresses the buffer spring in the receiver extension. The spring returns the carrier forward, stripping a fresh round from the magazine and chambering it. The bolt rotates back into position. The system is ready for the next cycle. What differs is what doesn't happen. In direct impingement, high-temperature combustion gases flow through the gas tube and enter the bolt carrier through the gas key. Those gases contain carbon particles, solid residue from incomplete combustion. That carbon deposits on the bolt carrier's interior surfaces, the bolt itself, and the gas rings that seal the carrier. Over hundreds of rounds, carbon accumulation creates friction and heat. Eventually, enough carbon builds up that the bolt can't rotate freely or the carrier can't move smoothly. The equipment requires cleaning. In the HK416's piston system, combustion gases never enter the receiver. They strike the piston, which transfers energy mechanically to the operating rod, which transfers energy to the bolt carrier. The gases themselves vent forward through ports in the gas block, exiting near the muzzle. Carbon still forms, but it accumulates in the gas block and piston cylinder, components that are easily removable and don't affect the bolt's operation. The engineering trade-off is mass and complexity. The piston system adds components: the piston, the cylinder, the operating rod, the gas block housing. Combined, these add approximately 10 ounces to the total weight. The gas block requires precise machining to maintain piston-to-cylinder alignment under thermal stress. The operating rod channel in the upper receiver is a proprietary feature that makes the receiver non-interchangeable with standard AR-15 uppers. But the operational gain is measurable. Test protocols showed the HK416 maintaining function through usage counts that would require multiple cleanings with a direct impingement M4. The system proved particularly advantageous in environments with fine particulate matter, sand, dust, ash, where contamination enters through the ejection port, but cannot reach the critical bolt-to-carrier interface because no gas tube provides a pathway. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. Reliability testing for small arms follows protocols designed to simulate operational stress. The HK416 entered those protocols in 2005, competing not against hypotheticals, but against documented M4 performance data. The sand test involved exposing the system to fine silica particles while cycling it through loaded magazines. The chamber remained open during dust exposure, allowing contamination to enter the receiver, a realistic scenario when equipment is carried in vehicles through desert terrain. The M4's direct impingement system showed degraded function after several hundred cycles, requiring disassembly and cleaning. The HK416 continued cycling beyond 1,000 rounds with the same dust load. The difference was clear. Without a gas tube channeling combustion byproducts into the action, the bolt carrier group remained cleaner. Temperature extremes tested thermal management. At -40 degrees, lubricants thicken and metal contracts. The piston-to-cylinder clearances that worked at 70 degrees could theoretically bind at extreme cold. The test protocol called for operation sequences after the equipment had been cold-soaked overnight. The HK416's piston system maintained function. The clearances had been engineered with thermal contraction margins built in. High-temperature testing examined what happened during sustained use, when barrel heat reaches levels that affect metallurgy. After rapid use, barrel temperature can exceed 500 degrees Fahrenheit. At those temperatures, thermal expansion becomes significant. The gas block, mounted directly to the barrel, expands with it. But the upper receiver, which houses the operating rod channel, expands at a different rate because it's not in direct contact with the barrel. The engineering challenge was ensuring that differential expansion didn't create binding or misalignment. The solution involved floating the gas block on the barrel with a specific torque specification. Too loose, and gas pressure could shift the block, creating misalignment. Too tight, and thermal expansion could distort the cylinder bore. The final specification represented a balance. Enough clamping force to prevent movement, but enough compliance to allow thermal expansion without inducing stress. Accuracy testing addressed a concern specific to piston systems: harmonics. Every barrel vibrates when used, a complex wave pattern called harmonic oscillation. The barrel moves in a consistent pattern that skilled users account for when zeroing their sights. Adding a piston system to the barrel changes the mass distribution and therefore the harmonic pattern. If that change is inconsistent, if the piston impacts vary in timing or force, accuracy degrades. The HK416 demonstrated accuracy comparable to or exceeding standard M4 performance. The key was consistency in the piston stroke. Because the piston moved the same distance every cycle and transferred energy to the operating rod at the same point in the pressure curve, the harmonic disturbance remained consistent. Users could zero the equipment and expect that zero to hold across different conditions. Endurance testing pushed the system to identify failure modes. Test units were operated continuously until components broke. The goal wasn't to prove the system would never fail. All mechanical systems eventually fail, but to identify which components would fail first and whether those failures were predictable and repairable. The HK416's piston and operating rod showed wear patterns but maintained function past 10,000 rounds. The bolt carrier, operating under lower velocity than in direct impingement systems due to the piston's mechanical advantage, showed reduced wear. The barrel remained the primary life-limiting component, consistent with all such systems. By 2006, enough test data existed to support fielding decisions. Specialized units, which have discretionary budgets for high-performance equipment, began adopting the HK416. Conventional forces, constrained by procurement processes and logistics infrastructure built around the M4, moved more slowly, but the engineering validation was complete. The piston system worked. The short-stroke gas piston system is the HK416's defining characteristic. But understanding why it matters requires understanding what it replaced. The AR-15's direct impingement system, designed in the 1950s, was elegant for its simplicity. No piston, no operating rod, no additional moving parts. The gas tube itself was the only addition to a basic rotating bolt mechanism. This simplicity meant fewer components to manufacture, assemble, and maintain. It also meant lighter weight, a significant advantage for equipment designed when reducing load was a priority. But simplicity created a dependency. The bolt carrier group had to remain clean for the bolt to rotate freely. In base conditions with regular maintenance schedules, this wasn't problematic. In extended field operations where cleaning intervals were determined by operational tempo rather than maintenance doctrine, carbon buildup became a failure vector. The HK416's piston system accepted additional complexity, more parts, more mass, more machining, to eliminate that failure vector. This wasn't theoretical engineering. By 2004, operational feedback from deployments had made the pattern statistically significant. Direct impingement systems required cleaning every 500 to 1,000 rounds to maintain reliability. Piston-driven systems extended that interval to several thousand rounds. In environments where access to cleaning materials was limited or where tempo made detailed maintenance impractical, that difference had significant implications. What makes the piston system the final curiosity is what it reveals about engineering trade-offs. The HK416 is heavier than an M4. It's more complex. It requires proprietary upper receivers that don't interchange with standard AR-15 lowers without the matching upper. It costs more to manufacture. By conventional metrics, weight, simplicity, cost, it's inferior. But those metrics assume maintenance is always available. The piston system's value proposition rests on a different assumption, that operational conditions will, at some point, prevent timely maintenance. Under that assumption, the complexity and weight become insurance. The piston system doesn't make the equipment better in ideal conditions, it makes it functional in degraded conditions. This design philosophy aligns with Heckler Koch's institutional history. The company built its reputation on equipment designed for reliability over elegance. The G3 was heavy and had significant recoil, but it worked in jungle, desert, and Arctic conditions. The MP5 was mechanically complex, but it fed reliably and maintained accuracy. The HK416 continued that pattern, accept compromises in ideal condition performance to ensure function in worst-case scenarios. The short-stroke designation itself is significant. Long-stroke piston systems attach the piston directly to the bolt carrier. The piston travels the entire length of the carrier's stroke. This creates more mass moving back and forth, which increases recoil and can affect accuracy. Short-stroke systems separate the piston from the carrier. The piston moves only enough to impart momentum, then stops. This reduces reciprocating mass and allows more precise control of carrier velocity. For the HK416, that precision mattered. The system had to maintain compatibility with standard AR-15 buffer systems. Buffer weight and spring rate are calibrated to specific carrier velocities. If the piston system accelerated the carrier too quickly or too slowly, it would require non-standard buffers, which would compromise the goal of maintaining parts commonality with existing M4 inventory. The short-stroke piston allowed the engineering team to tune carrier velocity by adjusting piston mass and stroke length until it matched the original timing. The final curiosity, then, is that the HK416's most important feature is also the least visible during normal operation. A user experiencing the equipment feels nearly identical handling to an M4. The piston strike happens too quickly to feel as a distinct event. The operational feel and manual of arms are familiar. The difference emerges only after hundreds or thousands of cycles, when the M4 begins to malfunction from carbon buildup and the HK416 continues functioning. The engineering triumph is creating reliability that only becomes apparent when other systems fail. By 2007, the HK416 had achieved something unusual in government procurement: adoption by elite units without formal competition. Operators with discretionary equipment budgets and direct experience with both systems were choosing the HK416. That choice represented validation more stringent than any test protocol. Users with direct knowledge of both systems preferred the piston-driven variant. The system gained visibility in 2011 during high-profile operations. That operational use created market momentum. Military units that had previously considered the HK416 too expensive or too different from standard M4s began reassessing. The question shifted from, is it better, to, is it worth the additional cost? For units expecting deployment to environments where maintenance would be constrained, the answer was increasingly yes. France adopted the HK416F as its standard service rifle, replacing older designs. Norway selected the HK416N for its armed forces. Germany's specialized units chose the HK416D5. Each adoption represented a national military determining that the piston system's reliability advantages justified the costs. These weren't incremental purchases. They were decisions to build logistics, training and armories around a system whose primary innovation was making the AR-15 platform more robust. The engineering legacy extends beyond adoption numbers. The HK416 demonstrated that successful development didn't require revolutionary technology. It required disciplined application of existing principles to documented problems. The short-stroke gas piston wasn't new. What was new was integrating it into the AR-15 architecture with sufficient precision that the result felt familiar to users while performing differently under stress. Other manufacturers responded. Multiple companies developed piston-driven AR-15 upper receivers. Some used designs similar to the HK416's short-stroke system. Others experimented with long-stroke configurations or hybrid approaches. The market validated that users wanted alternatives to direct impingement, even if it meant accepting additional weight and complexity. The HK416's design also influenced how organizations evaluated reliability. Test protocols began emphasizing sustained use and environmental contamination, rather than focusing solely on ideal condition accuracy and weight. The recognition that reliability under degraded conditions had tactical value shifted procurement priorities. A system that worked 95% of the time in perfect conditions but failed in dust or cold was less valuable than one that worked 95% of the time, regardless of conditions. The engineering represents a specific approach to problem solving. Identify the constraint, address it directly, preserve everything else. The HK416 didn't attempt to replace the AR-15. It didn't introduce new calibers or radical ergonomic changes. It changed the gas system because the gas system was the documented failure point. That discipline, the refusal to expand scope beyond the defined problem, is what made the project successful. Heckler and Koch's achievement was recognizing that improvement didn't require reimagination. The M4's manual of arms, magazine compatibility, accessory mounting and modularity were strengths. The direct impingement gas system was a weakness. Fixing the weakness while preserving the strengths created a system that institutions could adopt without comprehensive retraining or infrastructure changes. The HK416 works because its engineering respected operational reality. Users can't always maintain equipment on schedule. Environments contain dust, sand, and moisture. Sustained use generates heat and carbon. The piston system doesn't eliminate those factors. It isolates them from the mechanism that cycles the action. That isolation, achieved through mechanical precision and thermal management, is the engineering contribution. 3 decades after the M16 entered service, the AR-15 platform remained dominant, not because it was perfect, but because it was modular and familiar. The HK416 proved that dominance could accommodate improvement. The short-stroke gas piston, contained within a modified upper receiver, made the platform more reliable without making it unfamiliar. That balance between innovation and compatibility defines the system's significance. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.